Hi everyone, I'm Chivers. I'm a graduate student here at Georgia Tech in Earth and Atmospheric Sciences. I currently work on Europa with Brittany Schmidt, but as an undergraduate at the University of Idaho, I did a little work on Titan with Dragonfly Deputy PI Jason Barnes. And of the many really interesting things you're probably learning about Titan this week, we were really more focused on, at the time, Titan's dynamic surface, in particular its relationship to its climate and its methane and ethane hydrological cycle. And so today I'll just give you a little overview of some of the work I did on Titan to name Titan's North Polar Lakes. So as you probably already know by now, Titan is the only other body in the solar system other than Earth to have both an extensive atmosphere as well as stable surface liquids. And just like on Earth, Titan's atmosphere is really dominated by nitrogen, but it does have a really somewhat thick orangish haze layer that you can see in this visible image here. This orangish haze that you can see makes it really hard to see down to Titan's surface with the naked eye. But luckily, Cassini brought with it several instruments that were able to see through this haze and detect stable surface liquids that appear as these dark blotches in this image here. Unlike Earth, these liquids are not water because it's just far too cold in the outer solar system, so they're more likely to be something like condensed hydrocarbons like methane and ethane. And whereas on Earth, methane is a commonly used fuel in some applications, on Titan, this methane and ethane liquid is sort of an active participant in a cycle similar to Earth's hydrological cycle that is sort of illustrated here, where the liquid methane and ethane evaporate from the surface of these lakes and seas and make their way up into the atmosphere where they condense into clouds. Those clouds move around the surface and eventually rain back down to the surface, where that rain makes its way back to the lakes and seas, and the cycle starts over again. And just like on Earth, these rain events tend to carve channels, networks, and valleys as it makes its way back to the lakes and seas. And in fact, the Huygens lander that was on Cassini was able to see some of those similar things near the equator. But there were maybe also evidence for maybe longer term evaporation processes, because we see some things that look like dry lake beds. And even around lakes that currently have liquid in them, we see this bright red material in the infrared images that may be solid organics that left over from a longer term evaporation process. Around the active lakes, we sort of call it like a bathtub ring because it encircles the lakes. And this may be somewhat similar to what we can see in something like the Great Salt Lake in Utah, where it has a bunch of these salt flats surrounding the lake, and it's just a bunch of salt that is left over after the water evaporated. Most of the surface liquids on Titan are actually concentrated at the poles, and our first view of Titan Lake occurred at the South Pole by an infrared and visible camera on Cassini. At the time, it just seemed like some mysterious dark spot in the images, but later radar observations of the surface confirmed that along with their really unique lake-like shapes, there's probably liquid there that we know likely to be methane and ethane lakes. This first identified lake is actually called Ontario Locus, or Lake, and it's the largest lake in the South Pole. And it is, in fact, named after one of the 5 Great Lakes in North America, and is actually roughly about the same size. But to me, it's more memorable because it looks almost exactly like a foot. There are also a few smaller lakes in the South Pole, other than Ontario Locus, but the majority of Titan's methane and ethane liquids are actually at the North Pole. And they range from these really gigantic seas called Kraken Mare and Ligeia Mare, or Ligeia Sea, to relatively small lakes, which you can see both of these as blue dots and splotches in this false-colored radar image that's looking top-down at Titan's North Pole. These seas are probably a lot bigger than you'd think, and I don't think this image really does them justice, so I'll try to give you somewhat of a mental image of how big they might be. So Lake Lanier, if you're familiar with it, is one of Georgia's largest lakes, and it's roughly 13 times smaller than Ligeia and roughly 30 times smaller than Kraken. But maybe that doesn't quite get you there, so maybe a more apt comparison for these seas is actually the Great Lakes themselves. So Ligeia Mare alone is about the same size as Lake Michigan, one of the larger of the Great Lakes, and Kraken Mare is about the same size as at least 3 of the largest Great Lakes combined, and probably larger than that. But maybe a more intuitive comparison for both the Great Lakes and these Titan seas is actually the surface area that these Great Lakes cover is about the same as New York State, New Jersey, Connecticut, Rhode Island, Massachusetts, Vermont, and New Hampshire combined. And Kraken may be larger than that still. But other than these really gigantic seas, there is an area of the North Pole that we informally call the Lake District that hosts close to hundreds of smaller lakes that are those sort of blue circles in this false radar image I mentioned before. And while they're smaller than gigantic Kraken and Ligeia Mare, they're still pretty large in their own right, probably more like lakes that you're familiar with on Earth, as they range from about 5 to 100 miles across. So they're roughly about the same size as Lake Lanier, but there are hundreds of them concentrated at the North Pole, all in sort of one area. And most of them actually don't even have a name. So at the time, Professor Barnes's group was actually working on various projects related to the Lake District, and Professor Barnes thought it would actually be a good idea to name them. And of course, being the undergraduate in the lab, I was put up to the task. So to start naming these lakes, we wrote a proposal to the International Astronomical Union, or the IAU, who is generally responsible for keeping a record of and naming all important planetary features and their definitions. This and the IAU might sound somewhat familiar to you because they're the people who demoted Pluto from a planet to a dwarf planet. In any case, you're probably already familiar with a lot of name features on planets like Olympus Mons, the largest volcano in the solar system, which is on Mars, or Tycho crater, one of the largest craters on the Moon. And we generally name features like Olympus and Tycho just so they can be easily located, described, and discussed in the literature and elsewhere. This is, of course, especially useful when you're trying to discuss hundreds of relatively small lakes in Titan's Lake District, but names are really not just generally randomly given. For any different colored feature on a planet, there is a whole process, a whole standardized process to naming them. First part of the process is you can only really suggest names, and the names themselves have to fit a certain nomenclature or naming convention, and different bodies or planets in the solar system have different naming conventions or nomenclature for each feature. So for instance, craters on the Moon are named after scientists like Tycho Brahe, and here at Georgia Tech we have some people working on asteroid Ceres, where its craters are actually named after agricultural deities, like you may know Akator crater with its famous bright spot. On Titan, other features like the gigantic seas that we were talking about before are named after mythological sea creatures like the Kraken, a huge squid. The mountains on Titan probably have one of the best naming conventions that I've seen, as they're named after mountain ranges in the Lord of the Rings series. And so yes, if you're thinking, is there a Mount Doom on Titan? There is, and it's at the equator. The nomenclature of Titan's lakes, though, is maybe more boring, but it's probably more utilitarian given how many there are, in that they're named after lakes on Earth, just like Ontario Locus is named after Lake Ontario of the Great Lakes in North America. Second thing you kind of have to do is identify that they exist and measure their dimensions and find their location. And to identify them, make sure they exist, is we made sure they appeared in all 3 major data sets of Titan's surface. So the radar that you've seen, the infrared, and the visible wavelength cameras that I'm showing. We used at least 3 different flybys from the infrared camera, and all of the available radar and visible images of the North Pole. And across these 3 data sets, we of course measured their sizes, make sure they were identifiable in all 3, and that they were locatable. Figured out where they're sort of the center of each lake was. And through this process, we were able to identify, map, and roughly measure 60 individual lakes. By the time we were about to submit to the IAU, we cut down some weaker cases and submitted 40, with roughly half of them with suggested names. So after we submitted, of course, there was a review process with a committee over multiple months and some iteration with them back and forth, but less than about a year later, all 40 lakes we submitted were accepted and named by the IAU. So here I'm showing those lakes I identified, measured, and named. They're the underlined ones in that same false-colored radar image of Titan's North Pole from the top down, where, of course, the blue is the lakes themselves. Most of the names I picked, so like the 20 or so, were actually accepted by the IAU. So other than being listed on the IAU website now, some of those names I picked for those lakes have actually been talked about and used in the scientific literature. And at the end, to me, this project and this process really kind of speaks to me how important undergraduate research is and can be. On a personal level, it was part of the reason I decided to go into planetary science and help cement that love for it for me. And at the same time, it kind of demystified NASA missions from being these really large, inaccessible projects to something that I could actively participate in, even as an undergraduate. Like, to me, who felt like a little guy at little University of Idaho, this felt awesome to be part of the Cassini mission, who was doing like really amazing science at Saturn already in some way. And to be able to make a significant contribution to the Titan and the planetary science community, as well as that Cassini mission as an undergraduate, was like even better. So thank you for listening. I hope you enjoyed, and I hope you enjoy the rest of Titan at Tech Week. Thank you.